Today's topic for statistical mechanics is statistical ensembles. One of the reasons that we need to use statistical ensembles is because typically we're dealing with systems where we don't have complete information. We might have some knowledge about the system, but not complete knowledge. And so because of that, we have to use statistical methods. That means we have to consider and determine an average behavior of an ensemble or collection of systems. The working definition we're going to use today for a statistical ensemble is a collection of systems of the same structure as the actual system that we're studying, but distributed over a range of possible states, and we're going to make that more explicit by saying it will be over a range of, or over the range of accessible states that the system can be in. This is going to be a more formal lecture, but it provides a great deal of background at a rather high level. So let's get right into it. First thing I want to do today is to define the concept of phase space. Phase space is a conceptual Euclidean space consisting of two F dimensions. F refers to the number of degrees of freedom available to the system. By degrees of freedom, let's give an example. So suppose I have 10 molecules, each allowed to move in 3 dimensions. So they maybe can move in X, Y, Z directions. That would give me a total of 30 degrees of freedom for that system. Suppose I have N molecules, again allowed to move in 3 dimensions. Then I would have 3N degrees of freedom for N molecules, and so on and so forth. So one of the things that we need to know, of course, when we're studying a system, is the location of a molecule, or each molecule. But more than that, we also need to know what the velocity of each molecule might be. More specifically, we tend not to use velocity as much as we use momentum in statistical mechanics. And so we want to know not only position, but we want to know momentum. And you could imagine if we were to look at a system of, let's call position, let's designate it by the variable q, so that the ith molecule would have position q sub I, it would have momentum p sub I. And so what we would want to know then is if I have f degrees of freedom, I would have q1, q2, q3 all the way to qf positions, and then I would have p1, p2, all the way up to pf momenta. And if I were to look at any particular point in space, what we call phase space, we would do something like this. We would plot momentum on the y-axis and position on the x-axis, and a point then would designate the particular momentum and the particular position of a molecule or particle. And so this is what we call this graph of momentum versus position, is what we call a phase space graph. If I have an ensemble of systems, they might be represented by some cloud in phase space, where I might have these allowed momenta, these allowed positions, each one occupying a point in this cloud in phase space. And of course, this cloud over time is going to move through phase space because the particles all have momentum, and so this cloud will shift as we go through phase space. Or we can talk about a trajectory through phase space. Now, we might look at this as, one way we might think about this is, we could divide phase space into little tiny cells, where in those cells there would be some, let's say, uncertainty in the position, some uncertainty in the momentum, and we might know a particle's momentum and position within this uncertainty. Now, when we talk about this in classical terms, this could be arbitrarily small. For those who've studied some quantum theory, though, you know that the size of this box, the product of delta P and delta Q, is going to be somewhere on the order of h bar, or h bar over 2. So that's taking things a little bit far ahead of the course, but this should be at least somewhat familiar. Of course, this would remind us of the uncertainty principle in quantum mechanics. We'll get there much later in the course. So, for now, though, we're just going to consider a classical phase space, and I'm going to ultimately derive a theorem called Liouville's theorem, which will describe the motion of this cloud in phase space. One of the things that I want to point out very early on is that if we have this ensemble of systems, we're not so interested in what state a particular system is in, but we are very much interested in how many of those systems are in a particular state. It's not that we need to know one system from the next, but we do need to know how many. And that's going to be important to us as we go along. So what we want to do is talk about a probability density. And we've talked about this a little bit before. But I want to talk about it in terms of our ensemble. So we can have a probability density that is a function of all of our degrees of freedom of the system, all the way from P1 all the way to P final, if I have F, let's say, degrees of freedom in the system. Or I might write this for short, just Q, P, and of course, time. Don't want to forget time, as the system may evolve in time. I'm going to move this, let's start infinitesimally, okay? Let's talk about the probability density determining the number of systems we'll call delta n, which would be found at some time t to have coordinates and momenta lying within the range of a small range, delta Q1, delta Q2, delta P1, delta P2, all the way to delta PF, delta QF. Okay, so we're looking at this in an infinitesimal way. That's to say that I can write delta n as the probability density, Q, P, and T, times those quantities, dQ1, dQf, dP1, dPF. And we're going to look at the system as it changes. So, if we assume that delta n and the probability density can change continuously throughout phase space, we can change our summation to an integration, and I can write n as a number of integrals, rho of q, p, and t, dq1 all the way through d, f. N is the total number of systems in the ensemble. Now, this looks a little peculiar to you. Think about it in terms of maybe more concrete ideas, like suppose we could think of replacing n by a total mass. We could replace rho by a mass density, and dq through dp as by some volume. So if you want to think of something in terms of something that's more physical but very familiar to you, you might think of it in that way. Now, on the other hand, suppose, given this ensemble of systems, suppose we want to find a mean value of some physical quantity, some mechanical quantity, maybe pressure, for the systems in the ensemble. So suppose we call that quantity capital F. So we're going to write the average pressure or mechanical quantity, whatever it is a function of Q and momentum, is 1 over n times all of these integrals f of qp, rho of q, p, and t, and then of course dq 1 through dp. The double bar, notice, means a mean value over all the systems in the ensemble. If I had just one bar, it would mean the average value for a single system. But the double bar means the average over all systems in the ensemble. We could divide this by the integral of the probability density to normalize that mean. This typically, though, will always be equal to 1 because the probability over all space is going to be equal to 1. So we can erase then the denominator to make things a little bit less complicated looking. And this new mean would represent, again, an ensemble average for any quantity, for example, pressure. Well, one of the things that we want to be able to understand is how the probability density might evolve in time. In other words, how can we determine something about the change in probability density over time? And for this, we're going to derive Liouville's theorem. Okay. So let's consider a point in phase space that we can describe by coordinates q1 through qf, p1 through pf. And let's examine a small differential extension of that point, delta q1, delta qf, delta p1, delta pf, where rho is the density at that point in phase space. So we can write it in this way. We can write it as rho times these infinitesimals, these differentials, and we'll write delta n in that way. Now we understand that this number may change in time because the number of points that enter this, if you will, hypervolume may not be equal to the number of points that leave over time. So what we might want to do is let's take a more concrete explanation. So suppose we have two faces perpendicular to the q1. So here's the q1 direction, and we have two faces that are perpendicular to the q1 direction. And so we have one located at q1 and one located at q1 plus delta q1. So it's a concrete example. we might say that the number of points entering this region, we can write as rho times Q1 dot, that is dq dt, delta Q2, delta Q3, all the way delta QF, delta P1, delta PF. So this is the number of points entering. The number of points leaving over time, we can write as rho plus d rho dq1 delta q1 times q1 dot, that is q1 dq1 dt, plus delta q1 dot dq1 delta q2 delta qf delta p1 delta pf. Okay, looks complicated, but it will come out to be something that looks useful too. Of course, you could do this for every single position value, every single momentum coordinate as well. Of course, we're not going to do that. But if we did, we would find that you'd get a similar expression that we could put under a summation. So if we wanted to add up all those possible changes, points going into the region, points coming out of the region, it would look like this. It would look like d of delta n with respect to time is minus the sum over all my degrees of freedom, I equals 1 to f, rho dqi dot dqi plus dpi dot dpi plus d rho dqi dqi dot plus d rho dpi dpi dot dpi dot delta q1 all the way through delta pf. It's a mess. We can simplify this a little bit, however. These are p's, not rows. I'm sorry, these are rows. Sorry, rows, and these are q's and p's. By Hamilton's equations, you might remember from classical mechanics that we can write q dot as the derivative of the Hamiltonian with respect to momentum. Conversely, we can write momentum dot dp dt as minus the derivative of the Hamiltonian with respect to the position coordinate. What that means then is that the two left terms in the above equation cancel each other, and so we have a much simpler expression. So we can write d delta n dt is equal to d rho dt is equal to minus sum I equals 1 to f d rho dqi times qi dot minus d rho dpi times pi dot. So Liouville's theorem says that if I add this quantity on the left to this quantity, we'll just do that, bring that to the other side, set that equal to 0. This tells us how we can determine what statistical equilibrium is. What that means is that statistical equilibrium will occur when the probabilities of finding phase points in various regions of phase space and the average values of the properties of the systems are independent of time. How do we know this? Watch. Take a really simple example. suppose rho is uniform over all phase space. Okay, this is the simplest example. That means that d rho dqi is equal to d rho dpi. Both are equal to 0 because it's uniform. In other words, rho is a constant. By Liouville's theorem, d rho dt plus I f d rho dqi qi dot plus d rho dpi pi dot has to be equal to 0. We know that in a uniform ensemble, that's 0. That's 0. What means that it must be that d rho dt is 0 as well. And so this is Liouville's theorem for statistical equilibrium. What I'd like to start now, let's talk about some examples of statistical ensembles. We'll start with the really trivial to some that are quite a bit more complicated. First one, we only use this by comparison because it's boring as anything. This is called the uniform ensemble. We talked about that before a little bit. Literally nothing ever happens in this ensemble. In this case, rho is a constant. And again, we use this as kind of a control case. This is the most boring possibly. There's no interesting information. It's invariant to any kind of canonical transformations you can make. No matter what coordinate system you use, we will know absolutely nothing about the system. So, again, this is only used for comparison. First really important ensemble we consider, and will take us through the first part of the course, is what we call the microcanonical ensemble. So these are traditional terms. Don't often see them in the more modern textbooks. Nonetheless, it's definitely worth pursuing. It's often attributed to J. Willard Gibbs, but he is probably going to be more famous for the next ensemble that we talk about. This ensemble deals with conservative systems, namely conservation of energy, such that the energy is a constant of the motion. So specifically what this means is that rho, the probability density is 0, except in a range of energies, E to E plus delta. So we are to use the microcanonical ensemble, you have to be able to specify the energy very, very well, which is why it's not an ensemble that's used as much as some of the other ones. But it's also, there's a lot more to say about it. The more common and the easier ensemble to deal with, and we will deal with this much more readily later on in the course, is the canonical ensemble. And we can write this is a kind of an odd way to write the probability density, but I'm going to write it in this way. N times e to the power of psi minus e over theta. N is the total number of systems in the ensemble. E is the total energy of the system. E is still a constant of the motion. Psi and theta are called distribution parameters, and they're independent of Q and P. They're constants that have dimensions of energy. But as psi and theta change, so will the canonical distribution. And we'll begin with this at the beginning of next lecture.